The definitions of manifolds that we have given is admittedly quite abstract. Let us have a good understanding of these definitions by seeing several examples and non-examples of the type of objects that can be manifolds. Example number 1, we already saw this example, a special case of this, before we proved the implicit function theorem. This is the example of the unit sphere in R3. More generally, we can study the sphere of any radius, or rather let's fix the radius, sphere of radius r centered at the point a equal to a1 to an in Rn. So this is the sphere of radius r centered at the vector a1, a2 dot 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 an in Rn. So the equation of such a sphere is easily seen to be x1 minus a1 squared plus x2 minus a2 squared plus dot 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 xn minus an squared equal to r squared. This is from basic analytic geometry. You know that this is the equation of the sphere centered at the point a1, a2 dot 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 an of radius r. Now this is a manifold simply because look at the gradient of this function x1 minus a1 squared plus dot 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 xn minus an squared at some point y, let's say. Now this is just going to be 2x1 minus a1 squared. Rather, let's write y as y1 to yn, and we can just say this is going to be 2y1 minus a1 squared comma 2y2 minus a2 squared comma dot 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 2yn minus an squared. This is going to be the gradient vector, and this does not vanish. This does not vanish at any point of the sphere. So minor typo, I differentiated incorrectly. This is not square, just the 2 will disappear when I differentiate. Okay, so it's very clear to see that the sphere of radius r centered at the point a1, a2 dot 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 an in Rn is a manifold because at every point that satisfies this equation, we see that the gradient is going to be this, which clearly does not vanish at any point that satisfies this equation. So the sphere is a manifold. This is in fact a C infinity manifold. Okay, so this proves sphere is a C infinity manifold of dimension n minus 1. So the classical notation for the sphere of dimension n minus 1 is actually Sn minus 1. Okay, so this n minus 1 denotes the dimension. So that was the first example. The second example we are going to see is of this object that you see in front of you. This is a torus. So this is going to be a product. This is actually going to be a product. So let's just first consider the product of two manifolds and then specialize to this torus. So product of two manifolds. This is also a manifold. Well, if M subset of Rn and N subset of, so let me make this Rm, and N subset of Rn are CK manifolds of dimension d1 and d2 respectively, then this product M cross N, this is a subset of R m plus n, and it is a manifold. It is a manifold of dimension m d1 plus d2. Why is this the case? Well, if a comma b is a point in m cross n, then let phi1 and phi2 be local parameterizations near a and b, then this new function phi1 comma phi2. So let's say phi1's domain was u and phi2's domain was v. So this will be from u cross v to Rn plus 1 m is a parameterization, is a local parameterization near a comma b. Okay, so you just take two parameterizations and just sort of take their product, and you will get a parameterization of the product manifold. Okay, so this immediately follows that this product of two manifolds is a manifold. So this object that I have drawn here is called a torus. It looks like a tire or a tube or a donut or whatever. So this is actually supposed to be the product manifold. So let's take example number 3. The M torus, this is S1 cross S1 dot cross S1 M times. So repeating the argument in the previous part, we will get that this M torus is also a manifold of dimension exactly m, because we are taking m copies of S1 and taking the Cartesian product. Now what is this picture I have drawn here? Well, this is the 2 torus. This is the picture of the 2 torus. This is actually supposed to be S1 cross S1. So the way to imagine it is, you're taking one copy of S1, and just sort of revolving the other copy of S1 around this one copy of S1. Now if you think about it for more than a few minutes, you will realize that this S1 cross S1 is a subset of R4, and what we have drawn here is clearly a subset of R3. So in what sense is this the 2 torus? Well, for that we need to introduce the notion of a diffeomorphism and so on, which we will do in due course. But for the time being, you can check that this object that we have drawn here is also a manifold. We will later show that this manifold is diffeomorphic to S1 cross S1. So this is a good representation in R3 of the 2 torus S1 cross S1. So how do you check that this tube-like object is a manifold? Well, we can parameterize it. So there are 2 radii involved. Let the inner radius be capital R, and radius of tube be small r, and small r is strictly less than capital R. Otherwise things will go bad. You can imagine what will happen. So this inner radius is supposed to be this radius, the radius from the center to this, and this is supposed to be the radius, sorry about that, this is the inner radius, and this is supposed to be the radius of the tube. Okay, so the way I have drawn it, the inner radius looks smaller, so let me draw it in a different way. This is the inner radius, capital R, and this is small r. Okay, so what is this explicit parameterization of this tube? Well, you can write down a parameterization which need not be a global parameterization, but you're going to manufacture local parameterizations out of this sort of this function that I'm going to give you. So let U subset of R2 be 0 to 2 pi cross 0 to 2 pi. Okay, so this is just a rectangle in the plane. Let me, for convenience, let me just make it 0 to 2 pi half open. Okay, so the point 2 pi is not there in these intervals. So define G from U to R3 by R plus small r cos theta, then cos phi. Okay, so cos phi. So this is theta comma phi map. So I'm calling the variables theta and phi. So r plus r cos theta cos phi, then r plus r cos theta sin phi, then r sin theta. Okay, check that you can find local parameterization of every point of the tube using G. You will have to play around with G a little bit to do this. Every point of the tube using G. Okay, so this function G that we have constructed, that takes theta comma phi to this set of 3 points, r plus r cos theta cos phi, r plus r cos theta sin phi, and r sin theta. This is going to give you the local parameterizations that you need. Okay, so I'm going to leave it as an exercise to you to show that this tube is in fact a C infinity smooth manifold. Okay, now the next class of examples that we are going to see are graphs. Here are two graphs that are displayed for you. This is the graph of x squared plus y squared, and this is the graph of x squared minus y squared. This is known as the paraboloid. This is known as the hyperboloid. So these are figures that are very commonly studied. In fact, this paraboloid is used extensively in engineering, and this hyperboloid is used extensively in architecture. So these are objects that arise as graphs. We know that the graph is always going to be a manifold. So this is yet another example, graphs of smooth functions. Graphs of CK smooth functions. These are C infinity, by the way. CK smooth functions are CK manifolds. This is just by definition. A manifold is a more general object than a graph, so therefore graphs are going to be manifolds. Okay, now let's see some non-examples before we proceed any further. We want to see some situations where the object is not going to be a manifold. So let's say this is example number 5. The level set of the function xy at 0 is not a manifold. Okay, we have already seen this when we studied the implicit function theorem, that this object is going to be a cross and it's not going to be a manifold. More precisely, at this origin you cannot find a local parameterization, nor can you write this any neighborhood of this, nor can you write any neighborhood of that as a graph. Anyway, all three conditions are equivalent. If you cannot parameterize it, you cannot write it as a graph as well. So the level set of the function xy at 0 is not a manifold. Let's see another example where you have a function that's actually a graph, but it's still not a manifold. Look at graph of f of x equal to mod x. Okay, the graph is going to look like this. The graph is going to look like this. This is not a manifold precisely because we have demanded that there is some level of smoothness involved in the definition of the manifold. All three definitions that we gave involved functions that are smooth. Now, the function f of x equal to mod x is not smooth. Okay. Now that doesn't mean that it is impossible that f of this graph is a smooth manifold. That's not guaranteed. It could be the case that we could write this object, this v, as the graph of some other function which happens to be smooth. Okay, is that possible? Well, actually not so. It is not possible. It is not possible to write this v at 0 locally as the graph of even a C1 smooth function. It cannot be even a C1 smooth manifold. Well, why is that the case? Well, think about this for a second. If we could write this as a graph, let's say over some small neighborhood line minus epsilon epsilon, let's say for argument's sake, what is that function going to be whose graph is going to be this V shape in this neighborhood minus epsilon epsilon? If you think about it for a few seconds, you will realize that it has no choice but to be the graph of mod x, right? The function is determined entirely by its values. If you're going to write this v as a graph of a function, it's going to be the graph of mod x. Okay, so I want you to ponder over this simple argument to show that it's not possible to write this near this point 0 as the graph of a C1 smooth function. The function, if at all there is such a function, is forced to be mod x itself. So this is impossible. Okay, so what we have seen is some examples and non-examples of manifolds. Let's finish with one more example that comes from the level set. This is ellipsoids. These are ellipsoids. Okay, they are also graphs of functions. Okay, what is the function that is going to give rise to these ellipsoids? Let's just say that in R3 it's just x squared by a squared plus y squared by b squared plus z squared by c squared equal to 1. Okay, where a comma b comma c are numbers greater than 0. So x squared by a squared plus y squared by b squared plus z squared by c squared equal to 1. These will give you these various objects depending on the relationship between a, b and c, where you might even get a sphere, which is this case when a equal to b equal to c, and depending on how different they are, you might get different objects which are elongated, egg-shaped, almost earth-shaped also, where the earth is actually an oblate spheroid. So you get various objects which are somewhat like oblongated balls. Okay. Now let's concentrate our effort on understanding the relationship between the definition of of a manifold as locally being the graph of a CK smooth function, and the final definition of a manifold as an object that admits CK smooth local parameterizations. Both of these seem related. What is the precise relationship between these two? Well, first observe that being locally a graph automatically gives a parameterization. No additional effort is needed. So for instance, if f is from u to Rm and you want to parameterize the graph of this function, just consider x comma f of x. This will satisfy all the conditions needed for the parameterization. We briefly spoke about this in the previous video. Why will it be full rank? Because of this contribution of this x. Because of that, it's going to be full rank. Why is the inverse going to be continuous? Because the inverse is just projection. Inverse is just projection. So the graph gives rise to a parameterization, a local parameterization that has all the properties needed in definition 3 automatically. But if you in general take just a parameterization, that is just a function that maps onto a subset of the manifold, it need not satisfy the full rank condition, it need not satisfy that the inverse is continuous, so on and so forth. You need those conditions explicitly. So in the notes I have given several exercises to see what goes wrong if you drop some of these conditions. Okay, so there are several exercises I have given where things will look like it's going to be a manifold, but it's not. Please work out those exercises to get a good idea of what exactly goes wrong in some cases where an object is almost a manifold, but because one or two conditions are not satisfied, things go horribly wrong. Okay, so this is a huge bouquet of manifolds we have seen. I'm going to end with one more general example, that's the surface of revolution. But before I do that, I first want to consider curves as manifolds. Not all curves are manifolds. I believe this is example 7. For instance, look at this curve. This curve is not a manifold. At this point, it's things are going to go horribly wrong. There is no way to write that near that vicinity to write this as a graph of a smooth function. That's just impossible. So some restricted class of curves will indeed be manifolds. Okay, so let gamma from open interval AB to Rn be a C1 smooth curve that satisfies, well, I'm just going to tag on all the conditions I need to make this a manifold. So the first condition is gamma is injective, so that things like intersections and crossings do not happen and break local Euclideanness. So precisely what goes wrong at this point is that if you zoom in at this point, it's essentially the figure is going to look something like this. Okay, and this is not locally Euclidean. This does not look the same as an open interval. So in topological terms, if you know a bit of topology, these two objects are not homeomorphic to each other. Okay, so that's essentially what goes wrong. It's not locally Euclidean. Gamma prime of t is not equal to 0 for all t in AB. Okay, and the third condition is gamma inverse is continuous. So I have tagged along all the conditions needed to make gamma into a global parameterization. So such a gamma is also called a global parameterization of the curve. It turns out that all non-compact one-dimensional manifolds will have a global parameterization, but that I'm not going to prove in this course. Okay, so this is an example. Curves in higher dimensions give you examples of manifolds. In particular, I believe this is the very first example of a manifold in Rn which is not of dimension n-1. All the other manifolds examples that I have given are okay, not exactly. S1 cross S1 was 2-dimensional in R4, so I correct myself, but this is an example of a very low dimensional manifold sitting inside Rn. Okay, now you might wonder this, since I restricted gamma to be from open AB and not closed AB, what about the circle which we know is a manifold S1? Is that not covered? Well, that's also covered, but you cannot quite get a global parameterization of the circle, but you can get what is called a periodic parameterization. So that's defined as follows. A function gamma from R to Rn is said to be a periodic parameterization of the curve gamma of R if gamma has period L, I mean that this just means gamma of t plus L is equal to gamma of t. That's the meaning of the period. If gamma is period L, and of course this L should be the least number such that this happens, okay, least number such that this happens, and this period I'm requiring it to be greater than 0. I require the period L to be greater than 0. It's the least number such that gamma of t plus L equal to gamma of t for all t in R, and gamma restricted to t0 comma t0 plus L is a global parameterization. Global parameterization of gamma of t0 comma t0 plus L. Okay, so you cannot globally parameterize the whole curve, but you can parameterize almost the entire thing except the one point. So if you remove this one point, of course you can write this as the image of an open interval. You can do that, and you can check that this will be a manifold. Even if you remove this one point, it's still going to be a manifold. Check that that's indeed the case. You might think that these two portions of the circle getting arbitrarily close to each other is going to be a problem, but it will not be. It's still going to be a manifold. Okay, so global parameterization just means that it's a function defined from R to Rn, which is periodic transformation means it's a function gamma from R to Rn, which is periodic, and such that in each period interval it's going to be a global parameterization. Okay, so you can check that gamma of R is a of course a function smooth, C1 smooth is a C1 manifold. Gamma of R is a C1 manifold that is compact. Okay, so you can exhibit compact manifolds as images of periodic parameterizations. I want you to also find out a periodic parameterization of the circle. That's rather easy to do. Okay, so final example is that using these curves, I'm going to define a general manifold called the surface of revolution. That is, you essentially take a single curve and rotate it about a central axis, and you get a figure in R3, which not R3, in higher dimensions, which happens to be a manifold. Okay, now you can consider this torus also as a surface of revolution. What you do is you look at this circle, that is here, and you're just rotating it about this axis which goes through the center of this torus. Okay, center as in the center point of this torus. You're just rotating this entire circle about that single line to get the torus, the tube. Okay, so let's get back to our example, surface of revolution. How is this defined? Let P subset of R3 be a plane. Okay, I'm going to just consider surfaces of revolution in R3 for simplicity's sake, and let C subset of P be a curve that either has a periodic parameterization or a global parameterization gamma. So I'm considering a one-dimensional manifold C that admits either a periodic parameterization or a global parameterization. It turns out that any one-dimensional manifold always admits either a global parameterization or a periodic parameterization, but I am not going to prove this in this course. So that is usually shown in differential topology. that any one-dimensional manifold is either going to admit a global parameterization if it's non-compact and a periodic parameterization if it is compact. Okay, so let C be such a curve. Let L be a line that's also in this plane P, but L intersection C is empty. Okay, so take a line in this plane and such that L intersection C is empty. Okay, now what I'm going to do is revolve this curve in R3 about L. Okay, so what I'm going to do is so both L and this curve lie in one plane. So essentially what I'm going to do is I'm just going to visualize a third dimension that is perpendicular to this paper, and then lift this curve up and just rotate it about a circle so that this curve revolves around this line in three-dimensional space once. Okay, so if I were to finish this picture, if this were a circle like this, then if I do complete this procedure, I would get something like this, a tube. Okay, I've drawn it badly, but I hope you get the idea. I will sort of get a tube like the torus that we saw. I will get a tube sitting in R3. Okay, so I'm not going to prove in general that this is going to be a manifold. I'm just going to take a special case. I'm going to take a special case which reflects all the general ideas. Okay, so special cases P is XY plane and L is x-axis. Under these assumptions, I can assume that C is in the upper half plane. C is in upper half plane. That is, C is in the portion of the plane where y is greater than 0. Okay, think about why I can make this assumption. I'm going to give you a parameterization using which you can actually construct local parameterizations that satisfy all the conditions in the third definition of a manifold. So this is as follows. Let F equal to F1, F2 from AB to R2 be be a global or periodic parameterization of C. Okay, in case this is a periodic transformation parameterization, A and B would be minus infinity and plus infinity. Here I just mean any open set. It really doesn't matter. It could be any open set. Now I'm going to parameterize this surface of revolution M. Surface of revolution M can be parameterized by theta comma t. This maps to f1 of t, f2 of t cos theta, f2 of t sin theta. Okay, where theta comma t comes from 0 to 2 pi times AB. Okay, this is a global map. It will map onto the manifold M, and using this map you can construct local parameterizations of M that will satisfy all the conditions needed to show that M is a manifold. All the conditions of the third definition of a manifold will be satisfied. You have to modify this map a little bit, and I mean, this will not work globally. You will have to localize this map essentially. Okay, so there are a lot of things I've left for you to do checks. That's because getting your hands dirty and doing these computations and checking in fact that certain things I claimed are manifolds are indeed manifolds is probably the only way to learn this abstract notion of a manifold. This is a course on real analysis, and you've just watched the video on examples and non-examples of manifolds.